great pleasure to have our final speaker of the conference, Ofer Zeitouni from the Weizmann Institute. He's going to talk about partition function asymptotics for 2D random polymers in the subcritical regime. And we are lucky to have him for 2 months a year in Courant.
Thank you. Thank you for organizing this. It has been, sorry? I am the valedictorian. Okay. So I was going to say, I think that the first, I'm not sure that the first time I met Raghu was in Oberwolfach. Sorry? In Stanford? Maybe. I remember Oberwolfach. But yeah, that's not, that's of course true, but what I remember from that Oberwolfach meeting is not so much like everybody tells us about the great mathematical abilities of Raghu, etc., which of course they exist and we know them very well. But there's always this hike in going to San Roman to have a cake or something, and it was autumn and the days were short, and on the way down I was in a small group of 4 and we got lost. You remember that? You remember a time at Oberwolfach that you got lost coming back down? Yes, there was such an adventure, and Yao was with us. Yeah. And not only was with us, but as it was getting darker, Raghu was completely stoic. And Yao kept saying, "There are wild beasts in this forest. We are going to die." So anyway, so that's my Raghu story, which is not quite a Raghu story, but anyway. Anyway, so I'm going to talk about polymers. We have seen polymers the day before yesterday, and everything is going to be discrete. So, and it's going to be directed polymers. So those are the 2 attributes. In general, we have a graph, an infinite graph. We have on the edges of the graph IID weight, on the vertices of the graph, sorry, IID weights, which throughout this talk are going to be Gaussian, standard Gaussian. And then we have a random walk on the graph. And as that we are going to assume irreducible and as nice, very quickly I'm going to specialize the graph to ZD and Z2. And then we have a parameter which is the inverse temperature. And then we put a law on the environment, which is a tilting of the simple random walk law up to time n. And the tilting is simply by the weight accumulated along the trajectory by the random walk. And there is a partition function, which is a normalization factor here, which will be the most important thing, the important thing I'm going to be interested in, which is the expectation of this weight under the random walk measure started at a vertex V. Okay? And the crucial fact is that this is a positive martingale, so it converges almost surely. And the main question is, what is this limit? So under mild assumptions on the graph, you can show that this limiting random variable equals 0, there's a 0-1 law. It's equal 0 with probability either 0 or 1. And there is a critical value of beta critical, such that could be 0, such that if beta is in this, so I'm always taking, by the way, I'm always taking beta positive, because in this problem, beta positive and negative are the same. So there exists a critical beta, such that when beta is smaller than this critical beta, you have a positive limit almost surely, and when beta is larger than this critical beta, you get 0 almost surely. And we call this regime of positive limits the weak disorder regime. Now, there's another threshold, which is the L2 threshold, Of course, if the second moment is uniformly bounded, which may or may not happen, then Zn is uniformly integrable, and then the limit is positive almost surely. Beta 2 is the threshold, and this region, beta smaller than beta 2, is called the L2 region. Okay. Now, for general graphs, there are some surprises. So if you never thought about that in a general graph, just play this game in, not now, but in your mind. There are some surprises. For example, there is no monotonicity in the number of edges in the graph. You can show another thing that for me was a little bit surprising, that for percolation clusters on ZD, there is no weak disorder, no matter what D is. But now I want to specialize to the classical setup, which is ZD. And this goes back to physics papers, some of which were mentioned earlier, and then there was a lot of also mathematical work, of which the most important in Imbri Spencer and Bolthausen, who introduced to this game martingale techniques. And there is the fact is that in dimensions 1 and 2, there is no weak disorder. And in dimension greater or equal to 3, you do have a region of weak disorder, so beta C is positive. And very recently, there's a very nice work of Junk and Lacroix, who showed that in the strong disorder phase, the convergence to 0 is actually exponential. So you have a fast convergence to 0, so what is called a very strong disorder. And finally, this weak and strong disorder type properties, they manifest themselves not only in the partition function, but actually also in localization properties of the polymer. So, okay. And the last thing I want to say at the level of generalities, that for many people in this audience it's known and obvious, is that there is a link with the stochastic heat equation and with the KPZ. And so for the stochastic heat equation, if you rescale, if you take a modified noise and you rescale it in the following way in dimension greater or equal to 3, of course, this has a Feynman-Katz representation, which is essentially the same as the partition function of the, it's a continuous version of the partition function of the polymers that we saw. There's also interest in log U, and in dimension greater or equal to 3, in the weak disorder phase, there are lots of homogenization results. I put here some papers, but there are, it's really, the situation is relatively well understood. Okay. But now, what I want to do in this talk is to focus on the weak disorder regime in dimension 2, which I just told you does not exist. So what do I mean by that? So, of course, one can modify the model. And this goes back, as far as I know, to Bertini and Cancrini. But there has been, in the last 5 to 7 years, extensive work of this trio, and a lot of the results are going to be taken from that. The idea is that, yes, you don't have weak disorder, but maybe we can play with a beta parameter. And if we play with a beta parameter in the proper way, we will recover weak disorder. So what is a proper way? Well, introduce the green function. This is essentially the green function at 0, Rn, which is log n over pi, which is essentially the number of visits to 0 of a simple random walk by time n. And now rescale the beta by the square root of this parameter. Okay? So instead of taking beta constant, as we discussed earlier, which would lead to a strong disorder immediately, rescale it in this particular way. So this has some, and of course, once you do that, you can define Zn, and you can define Zn over x, which is the expectation of this object. So everything up to now for finite n, everything is well defined. One thing to note is that this is not a martingale anymore. So even the convergence is a priori not completely obvious. But it is true. So here is a theorem that was proved by Karavin-Hassan and Zigouras. If you look at the log of Zn, this converges to a Gaussian random variable. And the parameter of this Gaussian is written here. So remember, beta hat is this quantity that we rescaled by. There is a critical value, beta less than 1. So 1 is critical value in this parameterization. And when beta hat is smaller than 1, you have a central limit theorem for the log of Zn. Of course, Zn itself is a positive quantity, so it does not satisfy a central limit theorem in any way. And in fact, not only that is true, but all finite moments of Zn converge to those of the exponential of a Gaussian. So that's a stronger statement than the statement that I'm making here. The same results hold for the continuous model. So this is the boss of this trio, and also Jeremy, Gu, and Tsai have results on that. And more important, and maybe the most delicate mathematical work, is what happened at beta hat equal 1. So at beta hat equal 1, you can now do a second order expansion around this value of beta hat, namely take this factor with beta hat equal 1, and then plus another constant divided by Rn, not by square root of Rn, and look at what happens. And there's lots happening there that I'm not going to discuss today, although it's a very interesting and active field. The starting point that I'm going to take is in the weak disorder. So I told you I'm going to do weak disorder. We are in the weak disorder set. And we know that that this quantity, okay, converges to something that is Gaussian. And what I'm going to do, I'm going to blow it up. So this sounds a priori a bad idea, right? We have something that converges and is of order 1. I'm going to blow it up. Why am I going to blow it up? Actually, why did they blow it up? Because you can then show that this field, this is now a random field, but you see, I'm looking at x square root n. So it's kind of a random field on the box of size square root n. And this random field on the box of size square root n, so when x is in the unit square, say, converges to a logarithmically correlated field. Okay? And it converges to a fixed logarithmically correlated field multiplied by a constant here, square root of beta square. And this quantity G is a solution of Edwards-Wilkinson equation, so it's the other stochastic heat equation, the one with additive and not multiplicative noise. Okay? There are analogous results in continuous time. So Yu has some results on that. There are results of Nakajima and Nakashima and of these people. Okay. So we have that. I remind you that the point-weight limit of the log was this quantity lambda square, whereas here the limit is to something else. This is not lambda square. It's a different constant here. So I'm telling you this converges to a logarithmically correlated field. You would say, but the variances should match, but they don't. They don't in the sense that the constant here is not the same constant as we had for the pointwise limit, which is unusual for a log-correlated field. Now, when we say that it converges to a log-correlated field, I remind you what it means. It means if you take a test function, a smooth test function on this unit square, you integrate the left side, you get a random variable. You integrate on the right side, you get a random variable. Gaussian, the limits are the same. Okay? Good. So if you know me, you know that I see a logarithmically correlated field, at least in the last few years. I see a logarithmically correlated field, I get excited. So what do I mean by I get excited? I'm asking myself, okay, what can we say about the extremes of this field? Because after all, logarithmically correlated field, it's all a story of extremes. You can argue what kind of extremes. Are we talking about the maximum? Are we talking about thick points? Are we talking about things like that? But it's very often, it's a question of extremes. So if you want to understand extremes, the standard way, the standard approach is to start and compute exponential moments. So I remind you, this is a field. This is essentially square root log n. And we want to compute exponential moments of Gn. But of course, exponential moments are moments of Zn itself, but to power q, which is a high power, which blows up with n. Okay? So I told you before that if I look at finite moments of Zn, they all converge to the corresponding Gaussian thing. But now, if I want exponential moments of Gn, even, I don't know, e to the expectation of e to the power Gn, this corresponds to a square root Rn moment of Gn. So here is the first theorem I advertise. Forget about this condition. This condition essentially tells you that q is of order log n. Square root log n. So imagine that q is of order square root log n. Then you have an upper bound on the moment, which is a Gaussian upper bound. Okay? So you get exactly, this lambda was the right variance. So you get exponential moments according to what you expect. Okay? Those are questions about the statement. Okay. And so I de-emphasize the importance of this condition because now there are better results and this condition is not there. So the condition, this factor here is different. Okay. So as it turns out, this bound matches a Gaussian one, and as I will see you in the next slide, is also a lower bound. So in fact, everything is bound. Let me anticipate a little bit the future by saying that it will turn out, if you want to study extremes, that is maybe the main part of the talk, that is the main new thing in the talk that I want to convey. It turns out that it's not enough to compute pointwise bounds, and it's even not enough to compute some kind of mixed pointwise bound for 2 points, but you really need to understand expectations where you have here not the full sum, but part of the sum. Okay, so the sum here goes from k to k prime. Before it went from 0 to n, now it goes from k to k prime. Turns out the same method works also for that, and that's important. Okay? So I will tell you, if time permits, which I'm not sure, I will tell you something about the proof. But let me continue. This is a promised lower bound. So the promised lower bound is the same object with essentially the same Gaussian bound. Okay, so now if you are used to logarithmically correlated field, you know that to leading order, if you're looking for the maximum, it's completely given by the pointwise bound. Take the pointwise bound, compute the exponential, just take a union bound over n points in this square, and take a union bound by Chebyshev, given this exponential bound. That should give you the correct answer. Okay, so yes. So it turns out that this is not the answer. So it turns out that in this example of a logarithmically correlated field, the maximum is not given by the procedure I just described to you. And before I explain that, let me tell you a few words about the proof structure. I'm not going to bother you too much with it, but it's important to understand the rest. So if you want to compute the expectation of the moments of Zn, it's very simple. Since Zn has Gaussian weights in it, it's exponential of Gaussians, you know that it all comes back to some covariances. And when you compute it, you see that all you get, it's the same as the expectation with respect to to Q copies of independent random walk of the total number of pairwise intersections. And by using some a priori bounds that I'm going to skip, you can also move this lower sum here to some fixed s that grows slowly. For example, exponential of little order of square root log n. That's a technical step. Kosminski's lemma is a lemma that tells you that if you control the supremum of expectation in a Markov chain, you control exponential moments. That's Kosminski's lemma. It has other names. But, okay. The second thing that would be nice, that is crucial for our analysis, is to show that these kind of configurations don't occur. So what are these kind? Remember, you have Q, now that we have moved to this expectation, you have Q random walks. And it could be you're counting pairwise intersections, but it could be there are 3 random walks that intersect at the same time. It's pretty easy to show there are no 5 random walks that intersect at the same time, just by a priori bounds, but 4 and 3, you have to do something, and you can show that these don't contribute to the total sum. Okay. Now, once you have that, once you know that you don't have to care about triple and more intersections, the situation is that really you're talking about pairings of random walks, right? Because at each point only 2 intersect. So each time they intersect, you can think of it as a pairing. And in fact, you could imagine that you have a situation where 2 random walks pair, they go on intersecting for a while, and then each one goes to find greener pastures, to look for another match, et cetera, et cetera. So you can essentially, what is written here is essentially this idea, decomposing according to the matching times. But matching times, I mean new matchings. So if A matches B and then they continue to match each other for many intersections, this is not a new matching. I'm just looking at the beginning of a match and an instance of a new match, etc. So you get a diagram of this type. So you have pairs matching, you have, they go on together, and then maybe they go on their merry way, and then 2 others match, they go together, they go on their merry way, etc., etc. Of course, if you are following it honestly, this point could come a little bit earlier, namely these two guys here could meet again somewhere in this point. But each time there's a new matching occurring, I give it an index. So that's how we are counting matchings. And now you can write expressions for the moments, because here you have just the moments of 2 pairs. If I give you these times, AM minus 1 and BM minus 1, this is an expression that has to do with a pair of random walk. In fact, with a single random walk, because it's a difference, the number of visits to 0 of the difference, and you can write expressions for that. So you can write a big mess of expression to this, And I'm not going to tell you how you do it. You have a computation for random walk that enters into here. And you can kind of try to recurse it. Your first idea doesn't work. And then your second idea does work. I'm not going to say more about that. The lower, so basically you use these recursions, you use this idea of rewriting things in terms of intersections, and you do an induction on the number of pair intersections, dividing whether the new intersection is coming from the recent past or the distant past. That's the main technical tool that is needed. The lower bound is based on inserting appropriate, whoops, okay, I'm sorry. This was, I don't know what happened, but this used to be a full board. So I'm not sure what happened here. So this was a historical picture of my blackboard in my office where the whole proof appears, and that's what I planned to show you, but okay. The lower bound is based on an appropriate decoupling, so yes, okay. Very good. So I don't know what happened. Basically, you take well-chosen time intervals that we're going to call capital A. Okay, this is going to be, I don't know, sometime capital Li. And here, we are going to count intersections only in this little interval. And we are going to disregard these intervals in between. The idea is that these intervals here, where we close our eyes, will give us independence. And these intervals here will essentially capture the correct number of intersections up to an irrelevant constant. So I don't want to say more than that, except to say that at the end, the proof is based on a Poisson-type proof. So it's a second moment suffice for those who know what I'm talking about. And but one thing I do want to emphasize, if you compute a single interval during a time interval Li, what you discover is that the contribution of a single pair is of this form, 1 over 1 minus beta hat square log of L over log N. And you see here the fact that depending where the interval is, you get a different contribution. Okay? So that's a computation. You take two random walks, you ask yourself, I'm looking at an interval which is into the future, and I'm asking myself how many intersections, what is the exponential moment of the intersection, the normalized intersection, and it depends where this interval is. Not very surprising, but it depends in this particular form. Okay. So let me skip all that. And now let's come back to studying the extremes. So remember that I wanted to understand the n of x. Now, if there's a log-correlated field, there's a branching structure not far behind. And let me try to describe the branching structure. Where is the branching structure? So you think of the vertices x in the square as leaves of your tree. And now note that if you have two particles that start far away from each other, it will be a long time before they meet. They are not going to see each other for a long time. So that gives you immediately a tree structure. If you divide in dyadic scales your bottom thing, when you're very close together, you meet immediately. So you're very correlated because you see the same environment for all your way. If you start slightly larger in some mesoscopic scale, you see independent environments until you come together to time which corresponds to the square of the distance, and then you see the same environment. okay? So that gives you naturally a tree structure, and it's very natural to decompose the Z into ratios of the contribution to the partition functions coming from different time intervals. So that's exactly what is written here. So this is a contribution going from time n to the power k plus 1 over capital K, some large capital K, up to n, and this is for a slightly longer interval. And of course, once you write it like that, then log Zn is just the sum of these logs. Of course, those are not quite independent, but we saw in the proof of the lower bound how to make them more or less independent. So this tells you that the log of Zn should behave, and in fact we prove it does behave, like a sum of independent variables, but now coming back to what we said before, each one with a different variance. So in the, okay, when you do this contribution, you discover that the variance and the exponential moments and the variance depend on which interval you are at. And in branching random walk, some crazy people looked at this situation about 10 years ago. And it turns out that if your variance profile, so what do I mean by variance profile? Imagine that I'm looking at a branching random walk, so a tree, and imagine that my variance is a monotone function of the distance from the root divided by the depth of the tree. Okay? If that's the situation, and this function is decreasing, then the maximum is not given by the union bound. And the maximum is given by a solution of a variational problem. So this was done in the context of trees. And the leading order is understood. On the tree, with this kind of variance profile, we understand everything. We have limit laws, we have tightness, we have the Bramson correction is not Bramson anymore. It's not log n, it's n to the power 1/3. There are lots of things that you can say. So, Jeremy, this is another third that has nothing to do with anything. Sorry. So here is the end result. If you look at the maximum of this log of Zn divided by log n, it's going to converge to the integral of the variance profile. And that's a theorem that, okay, hopefully will be posted within the next month or so. Let me just make one concluding comment on this theorem, which is to go back to what I told you puzzled me from the beginning of working on this problem, which is we had this discrepancy of variances. So on the one hand, we had the pointwise variance, which was square root of beta hat square divided by 1 minus beta hat square. On the other hand, we had a log-correlated field, the log-correlated field had that as variance. On the other hand, the pointwise variance was this log. But of course, this log is just the integral of the pointwise variances along the trajectories, which was this expression. So when you compute the partition function, you get contribution from all scales, and you see that in the pointwise variance. But when you compute the log-correlated structure, if you don't ask about extremes, you just ask about integration against smooth test functions, you only see the macroscopic scales. You don't see the microscopic scales. They average out. So the only variance you're going to see is the first scale, which is beta hat square over 1 minus beta hat square. So in retrospect, we could have guessed everything just from this formula. We did not. We had to work hard in order to do it, but that's it. OK, I think I'm exactly on time. Thank you.